Okay, before the break, we have talked about the two methods, or not three type of methods available to estimating ODE parameters. First one is the nonlinear regression problems. The second nonlinear regression method. The second one is the two-step procedure. The third one is the Monte Carlo method. So now I'm talking about the fourth method, which is also my favorite method. I think this is so far the most satisfactory method available, called a parameter cascading method. So I will explain how this method is working. So basically, this is very similar to our smoothing spline method. Okay, so here we don't know the ODE solution, right? We cannot solve the ODE. We don't know the ODE parameters, and the ODE does not have an analytical solution. So what we can do is that we can use a smooth function to approximate the ODE solution. So here, this smooth function basically is a linear combination of basis functions. So here, I denoted the smooth function as f of t, and so here we have the phi k of t are the basis functions, and ck are the coefficients to the basis functions. So so we will choose the basis functions mostly using cubic B-splines, and so we will fix these basis functions. So in other words, phi k of t is known, right? So then we will try to estimate the basis coefficients such that this f of t will approximate the ODE solution. Okay, so how can we do this? So this is the picture for the cubic B-splines we have learned in our previous lectures. So here we actually have two type of parameters to estimate. So the first is the spline coefficients, the C here. So we call this as the nuisance parameters because they are parameters not of primary interest, right? And also we call this as the local parameters because the coefficients only decide the fate of the smooth function at the local areas. And also the dimension of these spline coefficients is large and increasing with the sample size. So generally, we learned that in the smoothing splines, the rule of thumb is that we will put one knot at each location with measurement, right? So the same principle applies here. So we will put one knot at each data point with observations. So the number of coefficients is roughly equal to the number of sample size, number of data points. And also, we have the other type of parameters are the ODE parameters. So the ODE parameters are called structural parameters because they are parameters of primary interest. And also we call that global parameters because these parameters are decided by the whole process, not just the local area. And also the dimension of these ODE parameters is small and fixed with the size of the data, right? So the number of ODE parameters generally is small numbers, and also these parameters will not change when you have more data, right? It's just fixed with the ODE models. So we estimate these two type of parameters with two nested levels of optimization. So in the inner level, we will estimate the basis coefficient C conditional on the ODE parameters. So for each given value of the ODE parameter beta, we will get an estimation for the basis coefficient C hat. So in other words, C hat is the function of beta, right? So generally, we cannot find this function C hat of beta analytically, but we know C hat is one implicit function of beta, right? And so because C hat is a function of beta, Where does the sound come from? It's from the other room? From that? Okay. So then the basic the basic function is c hat is the function of beta. So then in the auto optimization optimization levels, we will estimate the beta by minimize the criterion h. And here in this level, the basic coefficients are removed from the parameter space as a function of beta. So if we draw a picture diagram of the parameter cascading method, is that so basically for the outer optimization and inner optimization levels, they are iterated optimization. Okay, I will show you the program later on. So basically, we will first give the starting values for the ODE parameter, beta 0. And condition on this starting value of this ODE parameter, beta 0, we can go to the inner optimizations and estimate the ODE, estimate the spline coefficients until converge. After we get the ODE, the spline coefficients, we can find the gradient informations for the outer optimization levels and move to the next step. We can do this until converge. I will show you how we can find the gradient informations later on. So let's now first focus on the inner level optimization. So basically here we want to find this smooth function f of t, right? It's a linear combination of the basic functions. We want to find the basic coefficients to approximate the ODE solution, right? So this is our goals. So here we actually have two types of informations. The first is the data. We have the data, right? So we want to have this smooth function f of t to be close to the data, right? So this is obviously the goal. So then we measure the fit of this function of data by defining these sum square errors. This is exactly what we learn, we use when we do the smoothing splines, right? And secondly, we also want this f of t to satisfy the ODE as well as possible. So what can we do? So because f of t is a linear combination of the basic functions, so we can plug in the f of t into the ODEs, okay? And then we also know that the derivative of f of t will be equal to the linear combination of the derivative of the basic functions. So in other words, this is also a function of basic coefficients. So here, we will try to minimize the difference between the left side and right side of the ODEs. And we will define the fidelity of the smooth function f of t to the ODE by defining this integrated squared of this difference. So you can imagine if this term exactly equal to 0 means f of t is exactly the ODE solution. So we put these two criterion together, C1 and C2 together, and we add a tuning parameter lambda to control the trade-off between fitting to the data and the fidelity to the ODEs. And so here, you can we can look at the connection between this method and the smoothing splines. Recall that when we do the smoothing splines, we actually also have the exactly same form. What's the difference here? When we do the smoothing spline, generally we will using the second derivative to define the roughening penalty, right? In some cases, we can use the first derivative to define roughening penalty as well. That's fine, right? So in other words, generally, when we do the smoothing splines, this g function will set equal to 0, right? And then this will become exactly the smoothing spline method, right? And even when we estimate using the harmonic acceleration differential operator, this is actually that one is exactly an ODE differential operator. Exactly the same here. The only difference there is that we specified the parameter in the harmonic oscillatory differential operator, which is defined based on the period, right, of the process. So, but here, this beta is unknown. Questions?
Oh, I was just going to ask, so you said it's exactly the same as when we do
harmonic oscillatory differential operator.
The one before that, when you were talking about smoothing with the roughness penalty?
Yes.
But in the roughness penalty, we use curvature, right?
Yes.
But that's the second derivative.
Yes.
So it's not exactly the same, right? Because here
that's right. Yeah, we are using the first derivative. Okay. Yes. Yeah. Okay. Yeah. So not exactly the same. That's right. Yeah. So the ideas is very similar, right? Yeah. Yes. Yeah. Okay. And also here you can see that we're using this differential operator to measure this fidelity of the FOT to the ODE. So because we have this derivative of FOT, the FOT cannot be too rough. Okay. The reason because if you're too rough, you can imagine the derivative will become too big or too noisy, and then this difference will not be small, right? In other words, this fidelity term actually it also serves as the roughness penalty term. We're using the ODE to regulate the smoothness of FOT. Okay, so this is another function on this second term, C2 here. So for any given ODE parameters beta, we can estimate this C, right? The spline coefficients by minimizing this. And generally, if this differential operator is not a linear differential operator, we cannot find the closed form for the C here. So we have to do in this numerical method to find the C. But in any case, for any given ODE parameter beta, we can find the spline coefficient C. In other words, the estimation C hat is one implicit function of beta. Okay. So then we will look at the outer levels. In the outer optimization levels, we estimate the ODE parameter beta. So here we estimated the ODE parameter beta by trying to minimize the fit of the smooth function to the data. In the formula for the smooth function, it involved the spline coefficient C, right? But because the C hat is one implicit function of beta, therefore this criterion is also a function of beta, right? Yes. Okay. So here this kind of show you two unique aspects of parameter cascading method. So first, we allowed in different levels, we have different optimization criterion. Secondly, we allowed the functional relationships among these parameters. So here we will consider the relationship of C hat as one implicit function of beta. So what's the benefit to do this? The benefit is that when we do the optimization, we will use the Newton iterated method. So we know that in the Newton method, the computation will be much stable and fast if we can provide the gradient and Hessian matrices analytically, right? So by considering this functional relationship between these parameters, we are able to find out the analytic gradient. Although the C hat the function is only one implicit function of beta. So how do we do this? Just give you one example. So in the outer optimization level, in the H here, we want to calculate the derivative of H with respect to beta, right? We know that H is a function of C and beta. So then we can write down the derivative of H with respect to beta as the partial derivative of H with respect to beta plus the partial derivative of H with respect to C times the partial derivative of C hat with respect to beta, right? This is using the chain rule, right? So So we can find out these two partial derivatives with back to h, with back to beta, and with back to c hat analytically. That's no problem because you can write down the criterion h analytically, right? Yes. The only problem is this term, the derivative of c hat at function beta. The reason because we cannot write down the formula of c hat at function beta. We only know that c hat is one implicit function of beta, right? So how can we find the derivative analytically? This is hard. So any ideas? How can we find the derivative of c hat with back to beta? We don't know c hat, the functional form of c hat function beta. Okay.
It's the implicit formula.
Yes, this is very good. Yes. So we can use in calculus we have learned the implicit function theorem, right? So in implicit function theorem, you can derive that the derivative of c hat with back to beta actually is equal to minus the inverse of the second derivative of j with back to c times the second derivative of j with back to c and beta. Okay, so because we know the form of g as a function of c and beta, these two derivatives actually can be calculated analytically, right? Therefore, this derivative of c hat as a function of beta can also be calculated analytically, right? So this is a very, very useful. Then if you know this c hat function beta, if you can derive this, then you can derive the gradient analytically. So this is very, very helpful for using the implicit function theorem. It's a very elegant theorem. Any questions? Is this good? Okay. So in our criterion, there's also a smoothing parameter lambda, right? Yes. So how can we select the smoothing parameter lambda here? So this smoothing parameter lambda is different from the smoothing parameter in the smoothing splines. In the smoothing splines, we are trying to find the smoothing parameters that make the function smooth enough, right? That's the goal when we do the smoothing splines. But here, the goal is different. The goal here is we want to find the smooth function to be approximate ODE solution. In other words, the goal here actually we want to have this C2 term as small as possible. C2 is important to us, right? Because it represents the how close the smooth function f of t to the ODE model, right? Ideally, we want the C2 to be equal to 0, right? Yes. Okay. So therefore, here we want this smoothing parameter as large as possible. Okay. So this is the key point. So here we want to choose a large value for the smoothing parameter lambda, so generally we can choose the lambda equal to 10 to 6. Okay. Yes. We will force this C2 as small as possible. So if you compare to the smoothing splines is like put the smoothing the penalty as the second derivative to define the penalty, right? The SSE term actually is in the central part. We want to find the smooth function to close to the data, right? So for our setting here, C2 is our central goal, right? We want C2 to be as small as possible. Actually, this is C1 serves as the regulation term. We want this ft to be close to the ODE as much as possible. At the same time, we don't want the ODE smooth function to be too liberal that is far away from the data. Okay, so this is the difference between the smoothing splines. So how can we do this? So I personally find because here our goal is to find the ODE parameters such that the ODE solution with these parameter values will fit the data the best, right? This is our central goal, right? So what can we do? So we know that for each given smoothing parameter lambda, we can get the estimation for the ODE parameter beta hat. So in other words, beta hat is one implicit function of lambda as well, right? Yes. So therefore, I propose to estimate this lambda by compare the numerical solution of ODE with the estimated parameters to the data. So if we have some grid points on these smoothing parameters, for each given values for the smoothing parameter, we can solve the ODE, we can estimate the ODE parameter, the beta hat, using our parameter cascading method, right? After getting the parameter cascading estimation on the beta hat, then we can solve the ODE numerically, and then we can compare the numerical solution to the data. And we want to choose the ODE solution fits the data the best. Okay, and so this is like I will call this as a prediction error. The reason is because when we numerically solve the ODEs, actually we will starting from the initial conditions at the starting time points, and with the ODE parameters, we will solve the ODE numerically, right? So in other words, we don't using the other time points as the information. We just using the first time points to predict the whole process. Therefore, I call this as a prediction error. Okay, and so there will be no overfitting problem here. The reason is because for any smoothing parameter lambda, we always solve the ODEs with the parameter beta. In other words, the ODE will have the same set of number of parameters. It's different from when we do the smoothing splines. We can increase in the spline coefficients, overfit the data, right? So here, we always using the same number of parameters to fit the data. So therefore, there's no overfitting problems. Okay? And we also found that actually the ODE estimation is not very sensitive to the precise value of the smoothing parameters, as long as in a good range. Okay, so you don't have to working too hard to choose the best smoothing parameters. There's also good byproduct. Recall that for ODEs, actually there's a very important term for ODE solution is the initial conditions. You have to know the initial conditions to solve the ODE numerically, right? So you can see here in our parameter cascading method, we're using the smoothing functions, the linear combination basis functions to approximate the ODE solution. In the whole process, we actually don't solve the ODE at all, right? So therefore, after you get the smooth function, you can evaluate this smooth function at the starting time point, right? And you can use this estimated the value of this smooth function at the starting time points as the estimated initial conditions. So in other words, good byproduct of our parameter cascading method is that we are able to estimate the initial conditions from the data. Someone may ask me, why do you need to estimate the starting values, initial conditions? You can use the observed data at the starting time points as the initial conditions. It's true. The reason we think this is byproduct is very nice is because, firstly, when you're using the data at the starting time point as the initial conditions, we know the data always have noise, right? Have measurement errors. Therefore, we know that the ODE solution is very sensitive to the initial conditions. Therefore, we recommend you to using the estimated initial conditions. So actually in our practice we found that using the estimated initial conditions, the OD solution can fit the data actually better. Okay, so this is the reason we want to estimate the initial conditions, and also we know that in many OD systems, there will be some variables do not have data at all. In that case, you cannot have the measured initial condition. In that case, you have to using the estimated initial conditions. By the way, for this, another good advantage for this method is that it is able to handle the missing variables. So I will show you the predictor array systems. So that system is using this parameter cascading method, and it can able to estimate the parameters even there's two variables have no data at all. So this is the parameter cascading method. Any questions? Yes.
So we have inner and outer levels.
Yes.
It's like, can we make sure that each time we update beta and C, they're going to be converged to some.
You mean to how can we know? So Tianyi's question is how can we know the convergence of the iteration? Is this your question?
Right, because like for each inner level and outer level, we just update C or beta.
Yes.
But can we make sure that after each step, we may be closer to the.
Yes. Yeah. Yes. This is very good questions. So Tianyi asked, how can we know the convergence of these iteration steps? The answer is we cannot know. Okay. Yeah, it's hard to know. So I guess this is a problem. Yeah. So we haven't solved this problem yet. Yes.
Okay. So just to add on, like, so you just stop when you keep getting the same value over and over again to some significant digit? Or?
Yes. Yeah. That's what we're currently doing. So basically, so here we will set some tolerance of the change, right?
Okay.
So if the change of the parameters is very small, smaller than a threshold, like 10 to minus 3, for example, then we'll stop. Yeah, so this is the way we are doing here, but we haven't solved the guaranteed convergence problem yet. Okay, good questions. Any other questions? Okay, so let's stop here, and so after the let's have a 10 minutes break, and after the break I will show you how to do the programming in MATLAB for this estimating these OD parameters.